Hello everyone. This is part 2 of our Calculus 1 integration review. Last time we left off with the basic algebraic integration rules, substitution, and then we stated our integration formulas for the antiderivatives of the derivatives of the 6 basic trig functions. So remember, these are all on that one sheet summarized for you and available in Banner, or in Blackboard in the Exam 1 folder under Homework and Handouts. But these are considered common knowledge. There's the algebraic formulas, then the table that I suggested you recopy over and over until you memorize the derivatives as well as the integrals involving the trigonometric functions. And so basically, when integrating trigonometric functions, we have to first consider, does it fit one of the basic 6? So we'll be calling these formulas the basic 6, which are the antiderivatives of the derivatives of the 6 basic trig functions. So as we saw in the table, list the 6 trig functions, list their derivatives or their differentials, and then you could adopt the corresponding integration formulas. So these are what I will call the basic 6. So when we're faced with examples, first thing we look for is one of the basic 6. And in number 1 here, we see we do have a situation that involves the cosine of a function of x, so call it the cosine of u, and we have a basic formula for that. Even though the argument is rather simple, we still have to go through the formal u substitution. By choosing u to be the argument 5x, we calculate the differential du, which is 5 dx, modify, we get 1/5 du equals the differential dx, and when we look back at the integral, we have already established the cosine of u, but the du has to be satisfied. And if we looked at the leftovers, the only thing left in the integral is the differential dx, and comparing that to du, we see that dx is equal to 1/5 du. So we could replace that by 1/5 du, and now we've accounted for all of the factors of the integral so that we can make a complete change of variables. So most efficiently, we'll bring the 1/5 out in front, and change of variables, we get the integral of cosine of u with respect to u. And so we integrate, and integrating cosine, we get positive sine of u, add our constant of integration at that point, and then we back substitute. So just make sure you get your signs correct. You can always think of the reverse, right? I mean, we know integrating cosine should give positive sine, because if you take the derivative of sine, you get positive cosine. So make sure you get your signs, S-I-G and S, correct. And then back substituting, we have 1/5 sine of the argument 5x, which was our u, and plus our constant. Now, we want to adopt a general formula for this special situation, and I'm calling this special because the argument is rather simple. It's what we are going to refer to as a linear argument. So it's linear like mx plus b, so mx, or I'm going to call it kx. But when we have that situation, notice that if you change this number 5 to any other number, 7, 9, whatever, in general, we'll call it k, what's going to happen is the 5 is just going to become that other number, 7, 9, or k. So we could adopt a general integration formula, and we could say the integral of cosine of kx with respect to x is going to be equal to 1 over k times the sine of kx. So we get back the respective antiderivative, but just modified by 1 over k, and the linear argument stays. Similarly, the integral of sine of kx, we could do the same thing, and sine integrates to be negative cosine, but because of the linear argument kx, we just get a modification by 1 over k, so negative 1 over k cosine of kx. And this holds for all 6. I'll just list one more. For example, the integral of secant squared of kx Derivative of tangent is secant squared, so secant squared integrates to be tangent, but because the argument kx, you get a modification by 1 over k. And you could write out the other 3 if you like. But that's what I mean by the linear argument rule. And this is very important because in about 3 or 4 weeks, we're going to be integrating these types of things on a daily basis. And we don't want to have to go through the formal U substitution every time when the argument is linear, because we could adopt these basic formulas. Another reason why is if I give you a string of terms like the following example, if we did not accept the linear argument rule, we would actually have to make 3 separate U substitutions here, picking U to be cosine, or 6x, picking U to be 2x, and then U to be 5x. But the first thing we should consider is, we know when we have a string of terms that we can integrate term by term, and we know these constant multiples will just simply tag along in the differentiation process, in the integration process. That's our sum and difference and constant multiple rules. So our job is to make sure that the variable factors involved in each of the terms fit an integrable form. And they all do, because this is cosine, but moreover, the argument is linear, so cosine kx. Here's secant tangent, that's the derivative of secant. So we have a formula for that, but moreover, the argument is linear, so secant kx, tangent kx. And here's a cosecant squared, which is integrable. And again, the argument is linear. So therefore, we can integrate this in one step. The 3 is going to tag along as a constant multiple. Integrating cosine, we get positive sine, but because of the argument 6x, modified by 1/6, so 1/6 sine of 6x. Go to the next term, negative 4 tags along as a constant multiple. Integrating secant tangent, we get secant, but because of the linear argument 2x, modified by 1/2, so 1/2 secant 2x. And then the plus 10 tags along as a constant multiple. Okay, integrating cosecant squared, we get negative cotangent, but because of the argument 5x, modify by 1/5. So negative 1/5 cotangent 5x, and add our generalized constant. And I designed this so we get some nice cancellations here, just to make it look a little pretty. So 1/2 sine 6x, minus 2 secant 2x, and minus 2 cotangent 5x, and plus our constant, of course. Okay, but that is the only time that I'm going to suggest that you integrate by inspection, when the argument is linear and it fits one of the basic 6. If the argument is not linear, then we suggest a formal U substitution. So, like in examples 3 and 4. So, one thing is about algebraic and trigonometric functions. We're going to start to develop a hierarchy. Excuse me. A hierarchy for our integration scheme. And one thing we could say about algebraic and trigonometric functions is that in our little hierarchy, the trig functions dominate over the algebraics. So when we see an integral that involves a product of algebraic and trig functions, focus on the trigs first and ask yourself, does it fit one of the basic 6? Like in this example, I just focus on the sine and I ask, do I have a formula for sine of u? And we do. So therefore, we're going to try to fit that form by choosing u to be the argument, x cubed minus 1. Okay, this should be routine. The du is calculated, derivative is 3x squared. So in differential form, 3x squared times dx. We modify by the 3, so we have 1/3 du is x squared dx. And when we look back at the integral, we've already established the sine of u was the formula we were shooting for. We have to account for the leftovers, the x squared and the differential dx, if we compare that to our du, we see that they match. And we could replace the x squared dx by the 1/3 du. And take advantage of the fact that for this first exam, it's basically U substitution, but with a variety of different formulas. And the problems are designed to work. If you choose the correct formula to work with, and your choice of U is appropriate, your du will match. It's later on in the course, starting in exam 2, that we'll see situations where they don't match, and then we have to adjust our strategy. But right now, the problems are basically designed so they work. So getting back to this question, all the factors are accounted for. We'll bring out the 1/3, make the change of variables, integral, sine of u with respect to u. And I'm suggesting that you always bring it to a point where you have the basic formula, and then upon change of variables. And then there's just 2 steps left, integration and back substitution. Okay, integrating sine, that's negative cosine of u. At our constant at that point, notice how the integral symbol, the du, was dropped. Once we integrate, and we pick up the constant of integration, and then we back substitute, so negative 1/3 cosine of our u was x cubed minus 1, and don't forget to carry the constant. Okay, so trig functions dominate. But now here's a question that looks a little bit elaborate, because you got a fraction, and you got, the square root of t's in there, and secant squared, but you have to trust in our hierarchy. And the hierarchy says trig functions dominate over algebraics, no matter what the algebraic factor is. And so I see the trig function, and instead of writing it in this way as a quotient, as a fraction, I'm going to choose to rewrite it as the integral of 1 over the square root of t times the secant squared of the square root of t with respect to t. Because then the trig function is isolated to suggest our strategy, which is, again, that trig functions dominate. So if this is going to fit an integrable form, we would first consider secant squared of u. And look amongst the list, if you have to, look amongst the list of the integration formulas, the antiderivatives of the derivatives. Secant squared is there because it's the derivative of tangent. So we know we're on our way. We just have to follow through with the u substitution. Okay, we're choosing u to be the square root of t. Here we have to exercise a little bit of caution. First we have to rewrite as t to the 1/2. Then we differentiate, so du would be 1/2 t power 1 less negative 1/2, and formally the differential dt as well. And then we're going to modify by the 1/2, so you could think of dividing both sides by 1/2, or maybe more efficiently multiplying both sides by 2. So we have that 2 du is, and at the same time we do that, let's get rid of the negative exponent on t to the negative 1/2 and write it as 1 over t to the positive 1/2. And if that's not enough for us to see that what's left over here matches, you could even go so far as to rewrite this as 1 over the square root of t with respect to t. And then looking back at the integral, we look at the leftovers, the 1 over the square root of t and the differential dt, compare them to our du, and we see they match. That is, they make up 2 du. And so all factors of the integrand are accounted for. We're ready for a change of variables. Bring out the 2, and upon the change of variables, we have secant squared of u with respect to u. And secant squared integrates to be tangent of u. Add our constant at that point, and finally back substitute. So 2 tangent of our u was the square root of t plus the constant. Okay, so you got linear arguments. You can integrate by inspection. If the argument's not linear, then formal U substitution, fitting the basic 6. But then if it doesn't fit one of the basic 6, we got one more page for this review, then you have to try something else. And the things you could try, if the basic 6 fail, let me write that here, maybe as a little note. If the basic 6 fail, then here's your choices. First one, try to fit the form of u to the n with respect to u by picking u to be the entire trigonometric function that's being raised to a power. And then worst case, if that doesn't work, your favorite, trig identities. And of course I was being facetious when I said that as being your favorite. Okay, so in this example, number 5 that is, we see that it's not fitting one of the basic 6. And we know there's no product quotient rule for integration. All there is general power rule, in a sense, the integral of u to the n, our classic U substitution. And we can see that the cosine of 3x is being raised to the 5th. So we're going to try to fit the integrable form of u to the n by choosing u to be the cosine of 3x. Okay, now you have to be careful here. Make sure you put yourself in the differentiation mode. The derivative of cosine is minus sine of the same argument 3x, but then don't forget times 3, the derivative of the argument, and formally the differential dx should be tagged along. We could modify by the negative and the 3, so we have negative 1/3 du equals sine of 3x times the differential dx. And if we go back to the integral, now remember we were trying to fit the form of u to the n, choosing u to be the cosine of 3x, not the power. Our cosine to the 5th of 3x becomes u to the 5th. And if we look at the leftovers, sine of 3x differential dx, compare them to our du, and once again we see there's a match. We could replace sine of 3x dx by a negative 1/3 du. Okay, so now we're ready for the change of variables. Bring out the negative 1/3, and we have the integral of u to the 5th with respect to u. And so now we're ready to integrate. And so we have the negative 1/3, u to the 5th, integrates to be u to the 6th over 6. Add our constant of integration, and manipulate the coefficients, minus 1/18. If you put back substitute here, if you put back cosine of 3x in parentheses as a quantity to the 6th, I suppose that's okay, but in the future, I'm going to go right to shorthand and just simply write this as cosine to the 6th of 3x, plus our constant. So, again, if the basic 6 fail, try u to the n first. If that doesn't work, trig identities. So in number 6, okay, you might think I lied to you there because I said pick u if it doesn't fit one of the basic 6, which this does not. I told you to pick u to be the trig function, including the argument that's being raised to the power. But both secant and tangent are raised to powers. So which one do we pick? Well, we have to think a little bit. We know the du needs to be satisfied, so if we pick our u to be secant, think of its derivative, secant tangent. We have a secant, but we have way too many tangents. So if we think of picking u to be the tangent function, we know the du needs to be satisfied. The derivative of tangent is secant squared, and there's the secant squared that's going to help to satisfy the du. So in an attempt to fit the form of u to the n, we're going to pick u to be the tangent of 5x, not the power, because the power's going to be accommodated in the formula for u to the n, in particular in this case u to the 6th. Okay, the du is then calculated, derivative of tangent, secant squared, same argument 5x, don't forget times 5, differential dx as well. Modified, we get 1/5 du is secant squared of 5x dx. Okay, look back at the integral. We've accounted for u to the n, or u to the 6th in particular. What are the leftovers? Secant squared 5x differential dx. Compare them to our du, and we see they make up 1/5 du. So they match. Replace secant squared 5x dx by 1/5 du, and we've accounted for all the factors, and we are ready for a change of variables. Bring out the 1/5. Integral becomes u to the 6th with respect to u. And so we can integrate u to the 6th becomes u to the 7th over 7. 1/5 tags along, of course, and then plus our constant of integration. And manipulating the coefficients, we get 1/35. Back substituting u as tangent, so let's go right to shorthand. Tangent to the 7th of 5x, and then plus our constant. Okay, and as a final example, this integral of tangent over secant. Definitely not a basic form. There's no quotient rule for integration. Neither are raised to a power, so trig identities. So there's a little hierarchy scheme. So here we're going to use trig identities. And you might recall back in an algebra and trig class or pre-calculus class, when proving identities, one move was to change everything to sines and cosines. So I'm going to make this fraction bar thicker that corresponds to this fraction bar here in the original problem, and change everything to sines and cosines. Tangent is sine over cosine, so sine 7x over cosine 7x. Secant, recall, is 1 over cosine. Alright, then we'll invert and multiply. So the sine of 7x over the cosine of 7x times cosine of 7x over 1. So the reciprocal of the denominator. We can now cancel the cosines. And this was just the sine of 7x in disguise. And then this is a nice cute problem because this fits the form for the sine of u, but notice that the argument is linear. And so sine integrates to be negative cosine, but because of the linear argument 7x, we modify by 1/7. So negative 1/7 cosine of 7x and plus our constant. Alright, so that ends the Calculus 1 integration review, and when we come back, we'll be looking at integrals that result in natural logs.